Hello, and welcome to this course on effective data science. This week, we'll be considering effective data science workflows. These workflows are ways of progressing a project that will help you to produce high quality work and help to make you a good collaborator. In this video, we'll kick things off by looking at how you can structure data science projects and organize your work. Familiarity with these skills, processes, and practices for collaborative working are going to be instrumental as you become a successful data scientist. So, what exactly are we trying to do here? First up, let's take a step back and consider why we want to provide our data science projects with some sense of structure and organization in the first place. As a data scientist, you'll never work alone. Within a single project, you'll interact with a whole range of other people. This might be a project manager, one or more business stakeholders, or a variety of subject matter experts. These experts might be trained as sociologists, chemists, or civil servants, all just depending on the exact type of data science work that you're doing. And to get your project put into use and working at scale, you're going to have to collaborate with data engineers. You'll also likely work closely with other data scientists. For smaller projects, this might be to act as reviewers for one another's work, while for larger projects, working collaboratively will allow you to tackle larger challenges. These are the sorts of projects that you wouldn't feasibly be able to do alone, just because of the inherent limitations on the time and skill of any one individual human. Even if you work in a small organization where you're the only data scientist, then adopting a way of working that's focused on collaborating will pay dividends over time. The reason for this is that when you inevitably return to a project that you're working on in several weeks or months or years into the future, you'll have forgotten almost everything of what you did the first time round, and you'll also have forgotten why you made the decisions that you did that first time, and what the other potential options were that you decided not to take. This is exactly like working with a current colleague who has shoddy working practices. Nobody wants to be that colleague to somebody else, never mind to their future self. Even when you're working alone, treating your future self like a current collaborator, and one that you want to get along well with, makes you a kind colleague and a pleasure to work with. The aim of this week is to provide you with a guiding structure on how you organise and perform your work. None of this is going to be particularly difficult or onerous, however it will require a bit more effort up front and daily discipline. Like with flossing, the daily effort required isn't going to be large, but the benefits of these small efforts will compound over time. You'll get more done by wasting less time staring quizzically at a mess of folders and indecipherable code. You'll also get a reputation as someone who's well organised and good to work with. This promotes better professional relationships and greater levels of trust within your team, and these can then in turn lead to you working on more exciting and more impactful projects in the future. The structures and workflows that I'm going to recommend here and throughout the rest of this module are going to be strongly focused on a workflow that predominantly uses R, Markdown, and LaTeX. Similar techniques, code and software can achieve the same results that I show you here when coding in Python or C, or when writing up projects in Quarto or some other markup language. Similarly, different organizations are going to have their own variations on these best practices that we'll be going through together. Often organizations will have really quite extensive guidance on these topics. The important thing is that you understand what good habits are and have built them up in one programming language or business setting, and then transferring those skills to a new setting is then largely a matter of learning some new vocabulary or slightly different syntax. That said, let's get going. If there's one thing you should take away from this lecture, it's this one golden rule. Every individual project that you work on as a data scientist should be in a single, self-contained directory or folder. This is really worth repeating. Every single project that you work on should be self-contained and live in a single directory. An analogy here might be you're having a separate ring binder for each of your modules in a degree program. This one golden rule, equating one project to one directory, is deceptively simple. The first issue here is that it requires a predetermined scope of what is and isn't going to be covered by this particular project. This seems straightforward, but at the outset of a project, you often don't know exactly where the project will go or how it will link to other pieces of work within your organisation. The second issue is the second law of thermodynamics, which applies equally well to project management as it does to the heat death of the universe. It takes continual external effort to prevent the contents of this one single folder from becoming chaotic and disordered over time. Without external effort, entropy is always increasing. With that being said, having a single directory does have several benefits, which more than justify this additional work. So, what are the properties that we'd like this single, well-organized project to have? Well, ideally, we'd like to organize our projects so that they have the following properties. We'd like them to be portable, we'd like them to be version control friendly, and we'd also like them to be reproducible and integrated development environment friendly. There's a few new words here. Don't worry if you hadn't heard of some of these terms already. We're going to look into each of them in a little bit more detail now. Let's begin then with portability. A project is said to be portable if it can be easily moved without breaking. This might be a small move, like relocating the directory to a different location on your own computer. It might also mean a moderate move, say to another machine, if yours dies just before a big deadline. Or alternatively, it might be a large shift. It might need to be used by another person who is using a different operating system altogether. From this thought experiment, you can see that there's a full spectrum of how portable a project may or may not need to be, and the amount of effort is going to be proportional. A project under version control has all of its changes tracked, either manually or automatically. This means that snapshots of the project are taken regularly as it gradually develops and evolves over time. Having these snapshots as many incremental changes are made to the project allow it to be rolled back to a specific previous state if something goes wrong. A version control pattern also helps to avoid this horrendous state that we've all found ourselves in of renaming final version.doc to final version.doc and so on and so on and so on. By organising your workflow around incremental changes, it helps you to acknowledge that no work is ever finally complete. There'll always be small changes that need to be done in the future. In their paper, Broman et al. Define reproducibility as a project that you can take the original data and code used to perform the analysis, and then using those, recreate all of the numerical findings of that study. This definition does lead quite naturally on to several follow-up questions. Firstly, who exactly is you in this definition? Does it specifically mean you yourself in the future? Or should somebody else with access to all of that data and code also be able to recreate your findings? Additionally, should this reproducibility be limited to just the numerical results? Or should they also be able to recreate the associated figures, or reports, or press releases? Another important question is when this project needs to be reproduced. Will it be in a few weeks' time, or in 10 years' time? Do you need to protect your projects from changes in the dependencies, like new versions of packages or modules? How about the different versions of R or Python that come along over time? Taking this timescale out even further, what about different operating systems that don't exist yet, or different hardware? It's really unlikely that you'd consider someone handing you a floppy disk of code. It's pretty unlikely that you'd consider someone coming up to you today and handing you a floppy disk of code that will only run on Windows XP to be suitably reproducible. I mean, sure, you could probably find a way to get it to work, but that'd be an awful lot of effort on your end. That might be perhaps a bit of an extreme example, but it emphasizes the importance of clearly defining the level of reproducibility that you're aiming for within every project you work on. This example also highlights the amount of work that can be required to reproduce an analysis, especially after quite some time. It's important to explicitly think about how we're dividing that work between ourselves as the original developer and the person trying to reproduce that analysis in the future. A final desirable property is that we'd like our projects to play nicely with integrated development environments. When you're coding, documenting, and writing up your data science projects, It would be possible for you to work entirely either in plain text files or typing code directly at the command line. While these approaches to data science have the benefit of simplicity, they also have a great deal of expectations they're putting on you as a data scientist. This type of workflow expects that you should type everything perfectly accurately every time, that you should recall the names and argument orders of every function you use, and that you're constantly aware of the current state of every object within your working environment. That doesn't seem particularly realistic to me. And even if it is realistic, it's highly unnecessary. Integrated development environments, or IDEs, are applications that help to reduce this burden, helping to make you a more effective programmer and data scientist by reducing the number of things that you have to do at any one time. Let's have a look at a few of these things. IDEs offer tools like code completion and highlighting to make your code easier to read and to write. They offer tools for debugging to fix where things are going wrong. And they also offer environment panes that you don't have to hold everything in your head all at once. Lots of IDEs often have templating facilities as well. These are ways that you can save and reuse snippets of code that you can avoid typing out repetitive, boilerplate code and introducing human errors in the process. Even if you haven't heard of IDEs before, you've likely already used one. Some common examples might be RStudio for R users, PyCharm for Python users, or Visual Studio as a more language agnostic option. Whichever of these we use, we'd like our projects to play nicely with them, and this lets us reap their benefits while keeping our projects portable, version controlled, and reproducible for someone working in a different setup. So I've given a pretty exhaustive argument for why having a single directory for each project is a good idea. Let's now take a look inside that directory and define a common start and layout for the contents of all your projects. Having this sort of project directory template will mean that you'll always know where to find what you're looking for, and other members of your team will too. Again, before we start, I'd like to reiterate that we're taking an opinionated approach here and providing a sensible starting point for many projects. Every project can be slightly different, and some might require some slight alterations to what I suggest here. Indeed, even if you start as I suggest, then you might have to adapt your project structure as it develops and grows. I think it's helpful here to consider yourself as a tailor when making these changes. I'm providing you with a one-size-fits-all design that's great for lots of projects, but perfect for none of them. It's your job to alter and refine this design as you go for each individual case. These are just small tweaks you're making while retaining the same overall structure. One final caveat before we get started. Companies and businesses will many times have a house style on how to write and organize your code or projects. If that's the case, then follow the style guide that your business or company uses. The most important thing here is to be consistent at both the individual level and across the entire data science team. It's this consistency that reaps the benefits. Okay, caveats aside, imagine now that you've been assigned a shiny new project and have created a single directory in which to house that project. Here we've quite imaginatively called that directory Exciting New Project. What do we want to populate this folder with? That's exactly what we'll focus on in the rest of this video. I'll define a house style for organising the root directory of your data science projects in this module. Within the project directory, there'll be some subdirectories, which you can tell here are folders because they have a / following their names. There'll also be some files directly inside that root directory. One of these is called readme.md, and the other is called makefile or make.r. We're going to explore each of these files and directory in turn. So let's begin then with the readme file. This gives a brief introduction to your project and gives information on what the project aims to do. The readme should describe how to get started using the project and how to contribute to its development. The readme file is written in either a plain text format, so readme.txt, or in markdown format, readme.md, as we have here. The benefit of using markdown is that it allows some light formatting, such as section headers and lists, while only using plain text characters. Here you can see me doing that by using hashes to mark out the first and second level headers, and using bullet points for an unnumbered list. Whichever format you choose to use, the readme file of your project is always stored in the root directory and is typically named in all uppercase letters. The reasoning behind this is that the readme file should be the first thing that someone who's new to your project reads. By placing it in the root directory and capitalizing the file name, you're increasing its visibility and increasing the chances that this will actually be the first file someone looks at. An additional benefit of keeping the readme file in the root directory of your project is that the code hosting services where you might store your project, like GitHub, GitLab, or Bitbucket, will display the contents of that readme file next to the contents of your project. Those services also really nicely format any markdown syntax you use within your readme file. So using readme over plain text can make it a bit easier for a new user to read your documentation. When you're writing this readme file, it can be really quite useful to imagine that you're starting writing this for a new junior member of the team. The readme file should let them get started with the project and make some simple contributions after reading only that file. It might also link out to more detailed project documentation that will help that new team member toward a more advanced understanding, or making them able to complete a more complex contribution to the project. Let's take a quick aside now and see in more detail what we want to cover within this readme file. First up, a readme should include the name of the project, which should be self-explanatory, so nothing at all like my generic choice of exciting new project here. The readme should also give the project status, which is just a couple of sentences to say whether your project is still under development, the version of the current release, if it's already out in the wild, or towards the other end of the product lifecycle, if the project is currently in the process of being deprecated or closed down. Following this, we should also include a description of your project. This will state the purpose of your work and provide or link to any additional context or references that visitors aren't assumed to already be familiar with. What this is will depend highly on the context of the problem that you're working on. If your project involves code or depends on other packages, then you should give some instruction within the README on how to install those dependencies and how to run your code. This might just be text, but it could also include more interesting things like screenshots, code snippets, GIFs, or even a video of the whole process. It's also good practice to include some really quite basic examples of how to use the code within your project, and to give the expected results so that new users can confirm that everything's working on their own local instance of the project. Keep these examples as simple and minimal as you can, so that new users aren't burdened by unnecessary detail. For longer or more complicated examples that aren't necessarily in this short introductory document, you can add links to those in the README and explain them in greater detail elsewhere. Speaking about things getting more complicated, there should ideally be a short description within your README of how people can report issues with the project, and also how people can get started in resolving those issues or extending the project in some way for themselves. That actually leads me on to a point that I've forgotten to list here. There should be a section listing the authors of the work, so the people who've contributed to the project, and the license under which it's distributed. This lets you give credit to all the people who've contributed to your project, and the license file itself is going to say how other people may use your work. The license declares how others might use your project and whether they have to give direct attribution to your work when they modify and reuse it. Moving back to our project structure then, we next move on to the data directory. The data directory is going to have two subdirectories, one called raw and one called derived. All data that's not generated as part of your project is going to be stored in the raw subdirectory. And to ensure that the project is reproducible, data in the raw folder should never be edited or modified. In this example, we've got two different data types going on. We've got an Excel spreadsheet, the .xls file, and a JSON file as well. In the spirit of what we've just said, these files are exactly as we've received them from our project stakeholder. The text file metadata.txt is then a plain text file that explains the contents and interpretation of each of these raw datasets. This metadata includes things like descriptions of all the measured variables, the units that they're recorded in, the date that the file was created or acquired, and the source from which it was obtained. This raw data likely isn't going to be in a form that's particularly amenable to analysing straight away. To get the raw data into a more pleasant form to work with, it'll need some data manipulation and cleaning. Any manipulation or cleaning that is applied should be well documented and the resulting cleaned files saved within the derived data directory. In our exciting new project, we can see the cleaned versions of the previous datasets, which are now ready for modelling. And we also have a third file in this folder. This is data we've acquired for ourselves through web scraping using a script within the project that we'll see shortly. So here we have the two cleaned CSV files and that scraped data. The source, or src directory, contains all of the source code for your project. This will typically be the functions that you've written to make the analysis or modeling code more accessible. Here we've saved each function in its own R script, and in this project we've decided to use subdirectories to organise these functions by their use case. We've got two functions used in data cleaning here. The first replaces NA values with a given value, and the second replaces these by the mean of all non-missing values. We've also got three helper functions. The first two calculate a rolling mean and the geometric mean of a given vector, while the third is a function that scrapes that web data that we saw in the derived data subdirectory. Moving on then to the tests directory. The structure of this is going to mirror that of the source directory. And each function file is going to have its own counterpart file of tests. These test files provide example sets of inputs and the expected outputs for each function that we write. The test files are used to check edge cases of a function, or to assure yourself that you haven't broken anything while fixing some little bug or adding new capabilities to a function. And here we can see how that matches up with the source directory structure. The analyses directory is then going to contain what you probably think of as the bulk of your data science work. It's going to have one subdirectory for each major analysis that's performed. And within each of these, there might be a series of steps that we collect into separate scripts. The activity performed at each step is made clear by the name of each script, as is the order in which they're going to be performed. Here we can see the scripts used for the 2021 annual report. First up is a script that's used to take the raw monthly receipts and produce the cleaned versions of the same datasets that we saw earlier. This is then followed by a trend analysis of this cleaned dataset. Similarly, for the spend and review, we have a data cleaning step, followed by some forecast modelling, and finally the production of some diagnostic plots to compare these different forecasts. The outputs directory again has one subdirectory for each meta-analysis within the project. These are then further organised by the output type, whether that be some data, a figure, or a table. Depending on the nature of your project, you might want to use a modified subdirectory structure here. For example, if you're doing several numerical experiments, then you might want to arrange your outputs by experiment rather than by output type. The reports directory is then where everything comes together. This is where the written documents that form the final deliverables of your project are created. If these documents are written in LaTeX or Markdown, both the source and the compiled documents can be found within this directory. When including additional content in this report, for example figures, I'd recommend against making copies of those figure files directly within the reports directory. If you do that, then you'll have to manually update these files every time you modify them. Instead, what you can do is use relative file paths to include these figures. Relative file paths specify how to get to that image that you're trying to add in by starting from the location of your tech document and moving up and down through the levels of your project directory, rather than starting at the root or somewhere outside of your project altogether. If you're not using Markdown or LaTeX to write your reports, but instead use some online platform like Overleaf as a LaTeX editor or Google Docs to write collaboratively, then links to these can be added in the reports directory using additional readme files. If you're doing this, really make sure that you set the read and write permissions for those links appropriately too. When using these online writing systems, you'll have to manually upload and update your plots whenever you modify any of your earlier analysis. That's one of the drawbacks of these online tools that has to be traded off against their ease of use. So in our exciting new project, here we can see that the annual report is written in a Markdown format, which is compiled to both HTML and PDF. In contrast, the spend and review is written in LaTeX, and we only have the source for it. We don't have the compiled PDF version of the document, but that's okay, we can build it again from what's available here. Finally then, let's move on to the makefile. This is going to be the final element of our project structure. We aren't going to cover how to read or write makefiles in this course. I just want you to be aware that they exist, and instead I'll give a brief description of what they are, what they're supposed to do, and what we'll use as a workaround. At a high level, a makefile is just another text file. What makes a makefile special is what it contains. Similar to a shell or a bash script, a makefile contains code that could be run at the command line. This code will create or update each element of your project. The makefile makes things easier by defining shorthand commands for these full lines of code that could be quite complicated to create each element of your project. On top of this, the makefile also records the order in which these operations have to happen, and which of these steps are dependent on each other. This means that if one step or part of your project is updated, then any changes will be propagated through your entire project. This is done in really quite a clever way, so that the only parts of your project that are rerun are those that need to be updated. The reason that we're omitting makefiles from this course is not because they're fiendishly difficult to write or read, but rather because they require a reasonable foundation in working at the command line to be understood. What I suggest you do throughout this course, instead of making a makefile explicitly, is to create your own R or Markdown file called make. So make.r or make.md. In this file, you can define the intended run and order and dependencies of your project. And if you choose to use an R file, you might also want to automate the running of some parts of your analysis. And that completes our template project structure. Wrapping up then, that's everything we've got to cover in this video. I've introduced a project structure that will serve you well as a baseline for the vast majority of projects in data science. In your own work, remember that the key here is standardization. Working consistently across projects, within a company or a group, is far more important than sticking rigidly to the particular structure that I've defined here. But within this course, this is your structure that you should be following. While this structure gives you a good starting point for most data science projects, in your work in the future, beyond the end of this course, remember that the key here to getting any benefits is standardization. Working consistently across projects, across a company, or across a group is far more important than sticking rigidly to this particular structure that I've defined here. There are two notable exceptions where you probably don't want to use this project structure that I've suggested, and that's when you're building an app or when you're building a package. These require specific organization of the files within your project directory, and we'll explore the project structure used for package development during the live session this week. Thank you very much for your attention, and I'll see you in the next video.